lecture series on deep learning. In this lecture, we'll briefly discuss about what is regularization in deep neural networks and why we are going for this regularization. Introduction to regularization first. Why we are going for the regularization? In machine learning, models often perform very well on the training data but fail to give accurate predictions on the new unseen data. This is main drawback. This phenomenon is known as overfitting. Overfitting happens when a model captures not only true patterns in the data but also the noise or random fluctuations. Noise will also be added, random fluctuations will also be added. As a result, the model becomes too complex and specific to training set, leading to poor generalization. And regularization addresses this issue by discouraging the model from become overly complex. Next, what is regularization? Regularization is a technique used to improve generalization ability of machine learning model by adding a penalty term to the model's loss function. Penalty terms we are going to add to the loss function. And this penalty discourages the model from relying too heavily on any one feature or assigning excessively large weights. By doing this, regularization simplifies the model while retaining its predictive power, making it more robust to new and unseen data. Next, how regularization works. This regularization topic we have discussed very well in the previous lecture, AIML. If you want to know the detailed discussion, you go and refer that video, my video. Regularization works by modifying the cost or loss function. This function we can call it as loss function or cost function used in the training. The standard loss functions such as residual sum square or RSS means a residual sum of squares in linear regression is augmented with a penalty term. This penalty term is proportional to the size of the model's coefficient and is controlled by the parameter called here lambda. The updated loss function discourages large weights, thereby encouraging the model to find a simpler solution that still fits the data reasonably well. This leads to better generalization on data, test data. Importantly, this will discourage it. Importantly, regularization does not remove features from the model outright. Instead, it reduces the magnitude of their associated weights. This approach ensures that all features remain in the model, but their influence is scaled down. By reducing the impact of potentially noisy or irrelevant features, regularization creates a balance between bias and variance, leading to a more stable and accurate model. Next, linear regression. In linear regression, the model attempts to find the best fitting line or hyperplane through the data by learning optimal weights or coefficients for each features. The general equation is given by y is equal to beta not beta 1 x1 beta 2 x2 beta n xn plus b, where here the y this y is the predicted value. This y is the predicted value, and x1 x2 up to xn are the input features. X means input features. Beta 1 beta 2 up to beta n are the models learned weights. This is the models learned learned weights. B is the bias. The training process involves minimizing the residual sum of squares RSS, which measures the total difference between the actual and predicted values. However, in high dimensional data or when features are highly correlated, this approach can lead to large coefficient values and overfitting, which regularization seeks to control. Next, rich regression, L2 regularization. This we have seen it in the previous lecture. Rich regression, also known as L2 regularization, adds a penalty equal to the sum of the squares of coefficients to the cost function. The updated cost functions becomes cost equal to RSS plus eta into summation j to n beta bj theta square. Here lambda is a hyperparameter that determines the strength of the penalty. A higher lambda, not theta, higher lambda results in greater shrinkage of the here lambda value is high means a greater shrinkage of the coefficients, which reduces model's complexity and helps prevent overfitting. Rich regression is particularly useful when there is multicollinearity among features or even when the number of features exceeds the number of data samples. Unlike lasso, does not eliminate any features completely. It simply strings all coefficients closer to zero, maintaining all features in the model. Next, lasso regression. This we are calling it as L1 regularization. Lasso regression or L1 regularization modifies the cost function by adding penalty equal to modifies the, by equal to the sum of absolute values of the coefficient. Cost is equal to RSS plus lambda into summation j equal to 1 to n modulus of bj. This technique not only reduces the magnitude of coefficients but can also force some of them to become exactly zero. As a result, lasso performs both regularization and feature selection, automatically excludes irrelevant features, making the model simpler and often more interpretable. And lasso is especially useful only when only a subset of features are expected to be important or when we want a sparse model that avoids overfitting. Next, ridges versus lasso. The key differences: Rich and Lasso both aim to reduce overfitting, both reduce the aim to overfitting, but they do so in different ways. Rich regression uses L2 penalty, squared coefficients, and strings all coefficients towards zero without eliminating any. This makes a rich regression this makes the rich regression suitable when all features are potentially useful, when none should be removed completely. And lasso on the other hand uses the L1 penalty, absolute coefficients may be used, which is not only strings coefficient but also set some exactly to zero. This make it ideal for models that require feature selection or simplification. Therefore, rich is better for handling multicollinearity, while lasso is preferred when we want to identify, retain uh, only the most important features. Coming into the summary, why use regularization? Regularization techniques such as Rich and Lashock helps L1 and L2 regularization helps to prevent overfitting by discouraging overly complex models. This improves generalization by simplifying the model and controlling the impact of less important features. Rich regression, if you are taking, is effective when we expect all features to be useful and need to manage multicollinearity. In contrast, Lasso is ideal for producing sparse models by selecting only the most relevant features and choosing the appropriate regularization method based on the problem at hand can significantly improve the robustness and performance of machine learning models. And if you want to learn detailed discussion about regularization, kindly refer my the previous lectures which is available in AIML subject. So hope everyone understood about the basic concepts of regularization. The remaining things we'll discuss in the next lecture. Thank you.